let's look at the different types of reactions. So the first one is going to be the synthesis reaction. And the synthesis reaction is just going to be the combination of two or more chemical species to form a larger molecule. So the general structure just looks something like A plus B reacts to form AB. And so an example of this would just be the formation of water from hydrogen gas and oxygen gas. This fusion is synthesis. It's really one of the most straightforward types of reactions, and there's not too much you have to know besides the general structure. The fact that you have two molecules becoming one, you only have one product, is a pretty good sign that you're dealing with a synthesis. Now, decomposition is just now going to be the opposite of synthesis. Where synthesis was to build up a bigger molecule, decomposition is now going to be breaking down a bigger molecule. And that bigger molecule is going to follow this general template. AB becoming A plus B is decomposition, and the decomposition is the breakdown of a molecule that results in two or more simpler molecules. Now, at the same time, an example of a decomposition reaction would just be hydrogen peroxide. So hydrogen peroxide, if you have it in your house, it has an expiration date on it. And that's because hydrogen peroxide is relatively unstable and it will degrade into H2O, two of them, plus oxygen gas. So the fact that I have one reactant is a really good sign that I'm dealing with a decomposition. Now we get into a little bit more of the complicated ones. So now let's talk about displacement reactions. So there are two types. There are single displacement reactions and there are double displacement reactions. Single displacement reactions are a little bit more straightforward and you can't ask as much about them. So we'll kind of just go a little bit into single displacement before we get to the double displacement. So a single displacement is just a reaction where one element is substituted for another in a compound. So here we see that copper was originally a part of a compound. It was copper sulfate. But after this reaction, copper is now in a solid state by itself, while zinc replaced it. And so we had only one replacement happen. We had sulfate or copper sulfate that became zinc sulfate. So one change, single displacement. All right, so now let's focus on double displacement reactions. So double displacement reactions are just going to be reactions where two ionic compounds exchange their cations and anions to form two new ionic compounds. So these were also called metathesis reactions. And it's a popular way to refer to double displacement. So for this, we said that they're going to exchange their cations and their anions. So I have two compounds here, AgNO3 and KCl. If I just write out Ag and NO3 and then KCl, all that's going to happen is I'm going to kind of trade the partners. Here are my two cations, here are my two anions. They're all happy, except now they're going to switch. So K is going to bound to NO3 and Ag is going to bind to Cl, or kind of associate with Cl. They're ionic. So here we have AgCl now and KNO3. So that is a double displacement reaction. We've now traded the partners for these two ionic compounds. But it's a little bit more difficult than that when you actually think about what's going on. And so the reason that we're going to have to talk about this is you could be asked to write the net ionic equation for a double displacement reaction. So, to talk about the actual process of what goes on, we can't just use this nice little analogy for what a double displacement process looks like. We actually have to go in and look at the actual reactions or the actual reactants, and you'll notice that for both of the reactants, they have the symbol AQ, and that just means aqueous or dissolved in water. So why is this important? Well, when I put these molecules into water, they dissociate. The cations and the anions split. So if I actually wrote out what this looks like in water, so let's just say in H2O, I have Ag+, I have NO3, I have K+, and I have Cl-. And these are all aqueous, meaning dissolved in water. So for these 4 ions, they are going to be in the same solution, and that gives the opportunity for them to react with each other. Now, I would expect in an aqueous solution, all 4 of these aqueous ions are just going to stay aqueous. They're going to stay dissolved. But one of my products is a solid. So now that I have a solid, it means that 2 of my reactants suddenly became a solid. They came out of solution. And those 2 reactants were Ag and Cl. So after this reaction happens where AgCl becomes a solid, let's talk about what's going on in H2O. Well, I now have AgCl as a solid sitting in solution, but it's not actually dissolved anymore. But I still have the K plus that is aqueous and the NO3 that is also aqueous. Go in there and write down aqueous for me. Actually, you know what? I can't skimp on you guys. AQ, just for all of them except for AgCl. Whoops. So this would be called the complete ionic equation. We have every single one of our reactants shown. But there is something called the net ionic equation. Forget about this just because we're going to be focusing on this right now. Uh-oh. No, I should be all right. Yeah, all right. So, my net ionic equation is now going to be something different. The net ionic equation is a chemical equation that shows only the chemical species that directly react. I swear, no 2 of my letters that I write ever look the same. React in a given equation. So, did I have all of my actual original elements react? No, I didn't, because on this side of the equation, I have K plus and NO3 minus. They are aqueous, and I still have those kind of suspended in solution. They are still there, no reaction happened, while Ag and Cl came together, reacted, and precipitated. They even changed phase here. So because of that, Ag and Cl are only going to be part of the net ionic equation. They are the only 2 that reacted. So KNO3 is not here. The only net ionic equation, or the only elements in the net ionic equation, will be Ag aqueous plus Cl minus aqueous, which formed AgCl solid. So you really just need to look at the reactants compared to the products, write out the complete ionic equation, and then see what's different for the products. Because KNO3 was aqueous, and in the reactant side, those two ions that compose KNO3 were also aqueous, no change really happened. The only change was Ag aqueous, Cl aqueous became AgCl solid. So that is a net ionic equation.